In this video, we're going to continue our discussion on linear models with multiple predictors, and we're going to start with a model with two numerical predictors going back to our Paris paintings data set. And one thing I'm doing here as I read in the data is I'm creating a new variable called log price. Remember that in an earlier video, we talked about how price, the relationship between price and many of the other variables were fan-shaped. And also the distribution of price was quite right skewed. So that's why we're taking the log, and that's what we're going to use as our response variable. So we're going to fit a model to predict log price from basically the size of the painting. We're going to look at the width and the height. And again, are bigger paintings necessarily more costly? Maybe that's true if you have a giant mural or something, but also we've talked about how this is probably not how we measure the value of paintings. So we're taking a look at this model, starting with, again, setting up our linear regression, setting our engine, and then finally fitting a model, predicting log price from width and height, which are both given in inches in our data set. And here's our regression output that we can get to using the tidy function in tidy models. How do we, let's take a look at this. So if we were to write a linear model based off of this, basically what we have is our estimate for our intercept is 4.77. Our estimate for the slope of width is 0.0296. And our estimate for the slope of height is negative 0.0133. So we are seeing that price is expected to be higher as width increases, but lower as height increases, which doesn't make sense. Does it not make sense? It seems a little bit counterintuitive perhaps, but what we have here is probably a situation where our variables width and height, chances are, do not actually grow independently of each other. Because sure, as the width of a painting is bigger, we don't necessarily expect that its height will be bigger as well. But if we're thinking about big changes in width, chances are the height has increased as well. Otherwise, you could imagine having like a really wide painting that is really small in width, which doesn't really make sense. So some of what we're seeing here in terms of the coefficient estimates might be due to the fact that width and height might actually be correlated with each other. But this is how we would basically write our regression equation. And another thing I would like to show you is how would we represent this? So now we have two numerical variables that's predicting another numerical variable. In the previous video, we looked at a numerical and a categorical variable for predicting a numerical variable, and we were able to represent that visually using our x-axis for the numerical variable and something like a discrete scale colors for our categorical variable. We can't really do that anymore. So really what we're looking at is no longer a regression line, but really a plane, if you will, right? So we're basically seeing these points out in space, and we can kind of look around this and take a look to see where is the density of my points. Does it make sense that these the relationships are the way they are, that are estimated in our regression model? So this is just to show you that if we wanted to visualize a regression model with two numerical variables, we would really be thinking about fitting this plane. And what if there are more? Then we're actually we're working with bigger dimensions, in which case it's not really going to be as simple to visualize it as such. We would have to somehow project that onto 2 or 3 dimensional space that we can visualize in. I have provided the code for this visualization, that interactive visualization, not because I expect you to necessarily learn it and replicate it, but I figured some of you might be interested in how we would make something like this in R. So if you are interested, that code is provided there. Now let's look at another case where we have a numerical and a categorical predictor again. So we're going to look at predicting price from surface area and whether or not the artist is living. We want to first visualize and explore, and then we're going to model. And first we need to prep our data. Our artist living variable was coded as a 0, 1 variable, and 0 basically means the artist is deceased and 1 means the artist is living. So we're going to change this variable to be encoded as deceased and living, and we can look to see a large majority of the artists in the data set are deceased actually at the time of the auction, and a smaller percentage are living at the time of the auction. Here is what the typical surface area looks like for both of these types of paintings with deceased artists and living artists. So on top we have the deceased in orange, and then on the bottom we have the living in purple. The typical surface area appears to be less than 1,000 square inches, which is, you can think about that as like an 80 centimeter by 80 centimeter painting would roughly give you that. And there are very few paintings that have surface area above 5,000 square inches. So there is a tail, and it's so hard to see where those observations on the higher end are because they're just so faintly there, but it's hard to see exactly where they are. So what we're going to do is we're actually going to narrow our scope first and say we're going to focus on paintings with surface area that's less than 5,000 square inches, okay? Which is still huge. So we're just going to focus on those. So here we're seeing again the deceased artists represented with orange dots, and the living artists represented with purple triangles. We have them overlaid on the same plot here simply by color, defining the color and the shape aesthetics. But we might actually want to look at them faceted because there's so much data here that looking at it all at once is actually getting to be quite difficult to see due to all the overplotting that we're seeing. All the deceased values were overplotting the living, even though we had set an alpha level that's less than 1. So here we've basically both done the coloring and used the artist living variable for both the color and the shape, but we've also faceted by the artist living variable. So we can see here that if there is a relationship, that relationship might potentially be linear. We are seeing some like triangular kind of negative spaces in these plots, but also there's lots and lots of scatter. So we have, again, two ways to model this. Main effects, which would assume that the relationship between surface and log price does not vary by whether or not the artist is living. And interaction effects, which assumes that the relationship between surface and log price does vary by whether or not the artist is living. So including an interaction effect in the model will allow for different slopes, so non-parallel lines. This implies that the regression coefficient for an explanatory variable would change as the explanatory variable changes. This can be accomplished by adding this interaction variable, which is genuinely the product of these two explanatory variables. So here is the picture with the main effects and the interaction effects overlaid. In the main effects picture, we can see that the lines are almost overlapping. So their intercepts are off by very little by each other. And since we've imposed a structure with the parallel lines with the same slope, they're almost on top of each other, just off by just a little bit. In their interaction effects model, we are seeing that the purple one, so that's for the living artists, has a steeper slope, meaning that for living artists, as the surface area increases, the log price of the painting is increasing faster than for paintings by deceased artists. So let's fit the model with the main effect. So as usual, starting with a linear regression, setting our engine, and then remember that we're limiting our attention to the paintings that are less than 5,000 inches in surface area, and we're fitting the main effects model simply by using the formula log price versus surface plus artist living. And here we can take a look at our coefficient estimates. We have a slope, an intercept, a slope for surface area, and a slope for artist living as well. And this looks a little bit funny the way it's printed out here, but remember that artist living is the name of the variable in the data frame, so that's what's in the header of our column, and the deceased level is the deceased level is the baseline level, so the living level is the level for which the slope is estimated. And here is another look at basically that same output except in kind of written out as a model. The predicted log price is 4.88 plus the slope for the surface area times the actual surface area of the painting plus the slope for artist living times whether or not the artist is living or deceased. So we would plug in a 0 or a 1 depending on that. So how do we solve for the model? We basically can create two separate models, one for living artists, simply by plugging in 0 for the artist living variable, and one for deceased artists and one for living artists. And so this would be plugging in 1 for the artist living variable. And we can see that we can create these two models that differ by their intercept. They're off by just a little bit, but have the exact same slope because they're parallel. So mathematically, this is happening because when we plug in either a 0 or a 1 for the artist living variable, we end up getting either 0 in the first case or getting just the value of that slope that then gets added on to our intercept. So it basically shifts our intercept up because it has a positive slope, but it doesn't change the slope for the surface variable. If we want to, in terms of visualizing the main effects, basically what we're saying is that these two lines have the same slope. So the rate of change in price as surface area increases does not vary between living and deceased artists. They do have different intercepts though, meaning that paintings by living artists are consistently more expensive than paintings by deceased artists, according to this particular model. Again, this is not necessarily the reality. It is the model we chose to fit. And this is what this model is telling us. Now it's going to be on us to decide, is this what we think reality is, or is close to reality as possible that we feel happy with it, or should we be looking at these data in a different light? In terms of interpreting these numbers, so we have three numbers again to interpret. The 4.88, this tiny slope for the surface variable, and the slightly larger slope for the artist living variable. Remember here that we are actually predicting the log price. So these numbers are all in log livres, which is not super meaningful. So what we've done here is we've exponentiated all of them. So basically done e to the power of 4.88, e to the power of the slope for the surface, and e to the power of the slope for artist living. So the numbers we get are 132, 1, and 1.15. How do we interpret them? All else held constant, for each additional square inch in painting surface area, the price of the painting is predicted on average to be higher by a factor of 1. What does that mean? It's basically not changing. As the surface area is increasing, we're basically saying that we don't anticipate a whole lot of change in the price of the painting. Now, it's not exactly 1, it's just like rounded to 1, so I wanted to keep this number that we're using in the interpretation the same as the one here, but you can imagine it's just different by 1, just a tiny bit. And if we take a look at kind of these slopes, we can see that change, the slopes are not flat, but somewhat close to flat, but here they're on the log scale. So when we take a look at the exponentiated estimates, we're looking at them at the non-log scale. The second number, this 1.15, is about the difference between living and deceased artists' paintings. So all else held constant, paintings by a living artist are predicted on average to be higher by a factor of 1.15 compared to paintings by an artist who is no longer alive. So we're expecting the paintings by artists who are living to be more expensive, and more expensive by a factor of 1.15. given that we're looking at paintings with the same surface area. And paintings, and finally this number 132, paintings that are by an artist who is not alive is, is that right? That's our, right. So that is our actually baseline level, so paintings that are by an artist who's not alive and that have a surface area of 0 square inches, which doesn't really make a whole lot of sense, are predicted on average to be 132 livres. If we think back to the distribution of the price that we saw at the beginning of this kind of whole saga, that's not a very likely price to begin with, and because we're not going to have paintings with surface area of 0. So here's another situation where the intercept is not really meaningful. Now let's talk about main versus interaction effects. The way we specified our main effects model only lets artist living affect the intercept. The model implicitly assumes that with living and deceased artists have the same slope and only allows for different intercepts. But what seems more appropriate? Would it be more appropriate to have the same slope and the same intercept for both colors? So the lines would be basically overlapping. Same slope and different intercept for both colors, or different slope and different intercept for both colors? The first option basically means don't consider artist living at all. We could just give up on coloring the points and thinking about these as different groups, and we would just take a look at the relationship between surface and price. The second option, same slope but different intercept, says we would be looking at main effects model, but we would not allow the slopes to vary with varying surface areas, with varying artist living status. And the last one says different slope and different intercept, where we're basically saying that we're looking at an interaction model where we expect the relationship between surface area and price to be different depending on whether the artist of the painting is living or deceased. So here is that picture that we saw earlier brought back again with the interaction effect. So we are actually allowing, in this case, for the slopes to be different. And again, this is not necessarily reality either. We are fitting this model and then looking at what it looks like, and ultimately we might want to decide which one we believe more in, but there is no guarantee just because we drew these lines that this is actually reality. So in this case, our response variable again is log price, and our explanatory variables are surface area and artist living. One difference that we have in our model fit specification or model fit formula here is that we're using multiplication sign as opposed to addition. So when we do this multiplication sign, basically what R does is it also looks at the interaction between the two variables as well, and implicitly adds the main effects to the model as well. So when we look now at the estimates for slopes, we have one just for surface and one just for the artist living variable, but then another one for the interaction between the two. So by default, R basically takes a look at this formula and says, what you want is the main effects as well, so surface plus artist living, and their interaction. You can't have their interaction without having their main effects. So how do we actually work with this model? We can try to write out the linear model as kind of more of a mathematical formula. Our predicted log price is basically our intercept for 0.91 plus the surface area of the painting times the slope for the surface area, times either a 0 or a 1 for whether the artist is living or not, times the product of surface area and artist living multiplied by its slope. So how do we actually interpret these? What we're saying here is that the rate of change in price as the surface area of the painting increases does vary between paintings by living and non-living artists, so they have different slopes. Some paintings by living artists are more expensive than paintings by non-living artists, and some are not. And this is due to the different slopes. So these lines actually intersect at some point, and which one is higher or lower in terms of those purple and orange lines varies. So what we can do here is that we can again do that mathematical solving for the model. And we're doing exactly the same thing as we did before. For non-living artists, we're plugging in a 0, and for living artists, we're plugging in a 1, okay? Except the artist living variable now appears in multiple places, once on its own and once to be interacted with the surface variable. And so here, when we plug in a 0 for artist living, we basically end up with just the intercept, that's the intercept of the model, times the slope times the slope for the surface area. But when we do so, when we plug in the value 1 for artist living, again in both of these places, this ends up affecting the intercept and the slope. This is how we end up with these two lines that are basically different in their intercept and their slopes. It might be helpful if you wanted to pause the video at this point and in fact go back to where we outlined the model as a whole without doing any of the plugging in and work through this yourself as well. So literally take a pen and a paper and plug in 0 wherever you see artist living and solve for that, and plug in 1 wherever you see artist living and solve for that as well. Obviously, you're not going to be doing all of this like hand solving things to do predictions going forward. We're just going to use R for doing those. But it is helpful the first time you're encountering this to actually work through the mathematical solution for doing that, so you can convince yourself as to why we're getting these two lines with different slopes and different intercepts. And when it comes to comparing the models, we said earlier that we would like to compare the adjusted R-squareds of the model. So here I'm taking a look at the adjusted R-squared for the main effects model and the adjusted R-squared for the interaction effects model. And it looks like for the main effects model, my adjusted R-squared is roughly 1.3%. And for the interaction effects model, the adjusted R-squared is roughly 1.7%. So which one? It seems like in this case, the interaction effects are actually helping us increase our adjusted R-squared, which might mean that we might want to consider the interaction effect as well. It's not just overcomplicating the model. It is actually doing a better job in explaining the variability in the prices of the paintings. What about third order interactions? What if we had more variables? Should we interact them too? Can I? Sure. You know, you can interact whatever you want, but should you? Maybe, probably not. Probably not if you want to interpret these interactions in context of the data. So even with a two-way interaction, the interpretation gets a little bit dicey in terms of these, how to interpret those coefficients. You end up having to solve for the model to get the individual lines so that you can interpret their intercepts and slopes. With more levels of interaction, interpretation becomes harder and harder. But might there be a reason why you do that in a different sort of a setting? When we think about models that we use purely for prediction as opposed to interpretation, we might potentially think about not caring as much about the interpretability of our model and might take a look to see how can I actually just increase its predictive performance. So next week when we talk about more prediction, we're going to be saying a few more words about that. But for now, I think it's good for you to think about, for at least the purposes of this class, and really for when you're trying to stay in an area where you have simpler models that you're trying to interpret, going beyond the second level interaction may not always be a great idea.